All right, so let's rework this problem for the shear at D with the same loading, but now I'm worried about the shear at D. So remember, again, we'll use Mueller-Breslau. So I'll go to D and put in my weird little shearless connector. Remember that? And then we'll do positive shear on both sides. That should help me generate the shear at D. So this will be a quantitative. And then we'll go back and we'll put the values on it. So let me put a few marks here so to make it easier to draw it. All right, so let's start with the right side. If I push this up with positive shear, how is this piece going to move? Up or down? Up. And it's held down at E, so it has to go like that. If I push down on the left side with positive shear, this part of the curve, does it go down or up? It goes down. So you can see it's going to seesaw over C, and then the hinge at B will allow it to return back to where it's held down at A. So there's my shear influence line. Except for shear, we have some things that we know. What do we know? What's this change right here? It's going to be equal to 1. So let's see what we have here. So this is 5 feet, 5 feet, 5 feet. So if I found this value right here, what would be the value there? It'd be the same. This one would be positive, this one would be negative. Now this part of the curve is 5 feet, and this part of the curve is 10 feet. These are similar triangles. So since this is twice as big as this side, the height should be twice as big. So what number, when you add it to itself twice as big, is equal to 1? A third. So this would be minus a third, twice as big, 2/3. Add those together, you get 1. This is a third, this is a third. See, I don't even have any calculations to show you. It's just Mueller-Breslau to get the shape, knowing that these are similar triangles. If this has to be twice this value, that means 2 to 1. You add it together to get 3. It's got to be 1/3. Done. We don't have to do all that stuff like we did in the moment diagram where we have to go find internal moments and all that. It's a lot easier. Any questions about that?
So how do you know it's 2/3?
Well, I know. Let me do it a different way. Whatever this height is, h, right? This height has to be twice h, right?
Why?
Because it's twice as big. Because the base is twice as big as this base. These are similar triangles. If this is 5, this is 10. So this one's twice the size of this one. So if the height is h, this has to be 2h. And we know that 2h plus h has to be equal to 1. So that says that 3h is equal to 1, which says that h is equal to 1/3. H is equal to 1/3. This would be 2h, or 2/3. You guys may be making a little bit more out of this than it is. It's just pretty simple geometry.
Yes, the difference should be 1, right? Difference in height.
The change from here to here should be 1. And since we usually move from left to right, that means going from negative 1/3 to positive 2/3 needs to be 1. So now we just finished the problem. So we'll start with the concentrated live load. It has a value of what? 4 kips. Where should I put this to create the maximum shear at D. Yeah, it looks like the biggest value is 2/3, so really I'm going to place it just to the right of D. But I'm going to take advantage of that. So that means that my force is 4 kips, and I'll multiply it times 2/3, which ends up being 8/3, which ends up being 2.67. Is that right? 2.67, it'll have the units of kips. Remember, the unit of my influence line for shear is dimensionless. So this has no unit, and then to multiply by 4 kips, I get kip back again. All right, let's do the uniform live load. It's 300 pounds per foot, so that's 0.3 kips per foot. Now, I need to put that over all the positive areas. So that would be over this area, which is up from A to C, not from C to D because it's negative. But then I pick it back up and go from D to E. So I take care of all the positive areas. So they're both triangles. So there's my 1/2 for the triangle. And then I'll collect the area. So the first one would have a base of 10 feet times a height of 1/3. Plus the second one would have a base of 10 feet times a height of 2/3. The thirds combined to 1, you get 10. 10 divided by 2 is 5. 5 times 0.3 is 1.5. So that's 1.5 kips. Yeah.
And if the question was asking, determine the maximum negative shear, would we be doing the live load?
We can do both if you want. I got enough room. We'll do the negative value.
After?
Yeah. So let's finish. This would be the uniform dead load. Now remember, in the dead load, we don't get a choice. It goes over the whole structure. So I have to have positive area, negative area, positive area. The dead load is 0.2 kips per foot. And again, we have a bunch of triangles, so I'll put the 1/2 out front. So starting here, I've got a base of 10 feet, a height of 1/3. Next piece is a base of 5 feet, a height of minus 1/3. And then the third portion would be a base of 10 feet and a height of 2/3. Let's see, 10. No, that's going to be messy. Somebody's going to help me with that. 0.83. It sounds reasonable. Anybody else get that?
I just took the area we found before, which was equal to 5, without the 0.3, and then times the new area.
0.833.
What? 0.833? So let's add all those up. What do you get? So the moment at D, and I'll put positive next to it, is what? I guess that plus that. What is, go ahead.
4.0.
Say again? 4.0? 4.0. No.
No, that's 5.0.
What is it again?
5.003.
5.00. That's 5.
So I would just say, I just added it. So 5.
5. You were close. So let's do it again with the negative value. So I'll come over here and say, what changes? It's still 4 kips, except you multiply it not by positive 2/3, you multiply it by negative 1/3. So that gives me negative 1.33 kips. What happens with the live load? Well, I don't put it over the 2 positive areas, I put it over the 1 negative area. So that would be 0.3 kips per foot, again times 1/2, and we have a base of 5 and a height of minus 1/3. What's that?
Negative 0.25.
Negative 0.25?
0.
And then, of course, the dead load doesn't change. So add this, plus this, and what do you get?
2.41.
Negative 2.41?
Oh, yeah, negative. No. Hold on.
No, negative 0.7.
Yeah, you got that.
Negative point what?
7.4.
7.4?
7.
Yeah, close enough. What's the difference?
Thank you, Dr.
Okay, sounds good. That was an easy problem, I think.